In this video we're looking at database management systems, and this is section 8.2 in the CIE 9618 specification for computer science A level. So just to recap on the problems we had with a file-based approach, we got data redundancy and inconsistency. That means the same data was being stored across separate files or multiple times within a single flat file. For example, you might get student address stored in a fees file and an attendance file, and these can get out of sync, which causes the inconsistency. We had data isolation. Each application had its own file format, making it hard to write programs that pull data across files. And we had data dependence. The programs and the file structure were tightly related to each other. So if you changed the field or the layout of a file, it meant you had to rewrite the programs. And we had poor security and integrity control. So access control and validation had to be coded separately in every application, and that can become inconsistent. So the database management system tries to solve these problems in a number of ways. We have data management, data modeling, a logical schema, data integrity checks, and data security. So data management. The DBMS centralizes data, so all applications are sharing a single data store rather than maintaining a whole group of separate files. And the key mechanism here to do this is the data dictionary. So that defines the field names, data types, and the field lengths, any validation rules and constraints for each field, the relationships between tables with the foreign key links, and who is allowed to access which fields. And this metadata is stored once centrally. So that helps resolve the redundancy and inconsistency issue. Every application uses the same definitions rather than each maintaining their own. Data modeling. So this refers to representing data structures and relationships. Entities, attributes, relationships are all defined and demonstrated typically via ER diagrams, and this is done before implementation. That helps solve data isolation by explicitly mapping how entities relate to each other, so cross-referencing data, and that's designed in from the start rather than being bolted on. Then we have a logical schema. The logical schema describes the structure of the data, all the tables, the fields and relationships, independently of how it's actually physically stored on disk. And this is the basis of data independence. So we get logical data independence. The logical schema can change without affecting how application programs interact with the data. And we get physical data independence. The actual physical storage can change, i.e. different file organization or new indexes to files, without affecting the logical schema. And this directly solves the data dependence problem we had. Applications reference the schema and not go to raw file layouts. Data integrity. We need to ensure that data is accurate and consistent, and the DBMS enforces this through referential integrity checks, where foreign key values must match an existing primary key. It won't allow you to reference a student ID, for example, that doesn't exist. Entity integrity. Every table has to have a primary key, and that key can't be null. And domain validation constraints. So these are defined once in the data dictionary, for example the field type, the range check, presence checks, rather than being re-implemented on every single application that uses the data. And data security. The DBMS enforces access rights. So different users or groups of users can be given different permission levels. For example, read-only, read-write, but no access at all. This can be done at table or even at field level. For example, a receptionist might have read-only access to student records, but no access to to financial data, while an administrator has full access. It also provides backup procedures. Regular backups can be done by the DBMS, full, incremental or differential, plus transaction logs, so data can be recovered after failure without relying on each application to implement its own recovery logic. Now we come on to look at the software tools that are provided by a DBMS. The first one is the developer interface. The developer interface is a set of tools that it provides so that programmers can build applications on top of the database, rather than manipulating raw files directly. And this includes things like the APIs, which allow programs to connect with the DBMS without physical storage knowledge. Embedded SQL, so programmers can write SQL within their logic, within their program code logic. Form and report generators, which helps make input screens and reports. Stored procedure editors, so SQL logic can be created and embedded within the DBMS itself, so you only need to call it from there, you don't need to write it yourself. That reduces duplication of code to do the same things. Now let's have a look at some of the software tools provided by the DBMS. The first one is the developer interface. That's a set of tools that helps programmers build applications on top of the database, rather than them manipulating the raw files directly. APIs allow programs to connect with the DBMS without knowledge of the physical storage. SQL can be written into their normal program logic through embedded SQL. It also helps them make forms and reports, so input screens and reports are easier to make. And we have stored procedure editors, so we can actually put SQL logic into the DBMS itself, and therefore the programmers don't need to write that into their own applications. They can use the single copy within the DBMS. An example of an API connectivity driver is ODBC, Open Database Connectivity. And the idea here is that any application can communicate with any DBMS so long as that DBMS has an ODBC driver written for it. So this works via a driver manager. The application talks to the driver manager using standard ODBC function calls, and then the driver manager loads the correct driver for whichever DBMS is being used, translating generic calls into the DBMS's native commands. Now we're going to come on to SQL quite a bit more in the next section, but we need to introduce the idea here. SQL is a standard language used to communicate with a relational DBMS. It stands for Structured Query Language. Some people call it SQL and some say SQL, so I prefer to call it SQL. SQL is a declarative language. That means that the user or the programmer states what they want, not how to do it. So what data they want, not how to retrieve that data. The DBMS's query processor is responsible for working out the how. SQL commands fall into two categories: data definition language, DDL. These define the structure of the database itself, so when you're actually making the database or changing the structure of a database. And data manipulation language, which is how we read, actually ask questions of the database, put new data in, and so on. So DDL is for the structure and DML is to actually use the data. So the next tool we have within the DBMS is called the query processor. And this component takes a query, usually written in a high-level language like SQL, and turns it into an efficient set of operations that work against the actual physically stored data. It has a number of stages. So first of all, parsing, which is checking the query that we've written is syntactically valid and references tables or fields that actually exist. Query optimization. There are usually several ways of executing a query. For example, which tables to join first, which we'll see more about later. And the optimizer chooses the most efficient execution plan based on stored statistics about table sizes and index and so on. And then execution. It carries out the optimized plan against the physical data and returns the results set to whatever issued the query. So some key points. The DBMS and associated tools provided by the developer interface make it much simpler for programmers to access and manipulate data in a reliable way, regardless of how that data is actually stored physically and regardless of which particular database is being used. The DBMS helps keep data secure and maintain its integrity. SQL is the language used to express a request. The query processor is the DBMS component that receives that request, parses it, optimizes it, and executes it. And that's the end of 8.2. Next time we'll look in more detail at SQL and do DDL and DML. Thank you very much.